So, hello everyone. I'm Biagio Di Mauro from the Institute of Polar Science in Italy, the National Research Council of Italy. My lecture today will be about snow and ice, albedo and grain size. There's no ice in the formal program. Since I work a lot also on ice, I put some material also on ice, since the course is on snow and glaciers as well. So the presentation is structured in this way. I will give a brief introduction about what I mean with albedo and grain size of snow and ice. You will see that the term is quite broad, and each different communities use the term in different way. We will try to make some order out of this. I will briefly review the imaging spectroscopy and radiative transfer modeling of snow and ice. So what I want to share with you is how to interpret the spectral reflectance of snow and ice when you look at in satellite imagery or aerial imagery, whatever. So at the end, there is quite a long part of sample application of Sentinel-2, Sentinel-3, Prisma, and Nmap. You will learn about this hyperspectral mission. Maybe Marco Celesti already did a lecture about on Monday about CHIME. So these are, let's say, precursor of this imaging spectroscopy mission from ESA. So I think it's important to know what has been done with this kind of instrument, and what it will be done in the future with CHIME and SBG and so on and so forth. The application will be in the Alps, in Greenland, and something about Antarctica as well. On the Earth, we have quite a different type of snow and ice, and all of this type have different optical and thermal properties. So when we study snow and ice, we must have in mind what we are studying and what are the type of snow and ice that we are looking at. Since, for example, snow is the result of meteorological forcing, and this changes a lot the optical and the microstructural properties of snow and ice. So I will briefly touch not all of this snow and ice type, let's say, but many of them, in order to show you how they changes as a function of latitude, altitude, and location. What are the differences between polar snow and ice and alpine snow and ice, and so on and so forth. Let's start with the basics. So ice, glaciers and snow, they mostly start with ice crystals formation, and the ice crystals show very different geometrical shape as a function of the where and when they are formed in the atmosphere or on the surface. As you see, there is quite a big complexity of the structure of a snow crystal or an ice crystal. So studying the optical properties of this object becomes really, really complex and hard, also for a mathematical point of view. So the first approximation that I will take for the whole presentation is that, for me, this structure on the right of the slide are spheres. So this is quite a big approximation, because like physics that works in the optics will have a heart attack after this, this statement. But for remote sensing and retrieval of parameters, the most common approach is to approximate the crystals as spheres. So we will see that in some cases, when I will speak about SSA, the snow-specific surface area, I will also look into the structure of the crystal. But mainly, I will speak about the grain size, and I will refer to the diameter or the radius of the sphere that approximate the snow crystals. So the larger are the spheres, the longer is the path of a single photon into the snowpack or glaciers. So it will be most probable that this photon is absorbed or transmitted rather than reflected. So larger grains means lower albedo, so more absorption and less reflection to the atmosphere. And we will see some examples about this. There are different, as I said, optical properties of snow and ice. We have to keep in mind that there is a whole world about different ice and snow types. But in first place, see the pointer, yes. You have the snow that is mainly built up of air. So there is a lot of air inside of snow and a lot of scattering events. So the snow is reflecting most of the radiation that is coming from the sun. So when we think of a glacier, for example, as we go deeper in the glacier, the snow will be more and more packed and less air will be present on the glacier. So when we go through the fjord and the ice, we will have a much more absorption of the light and less reflection. In fact, if you think of a pure block of ice, you can see through. So there is no much scattering event through my eyes. Most of the light is transmitted through this block of ice. Instead, if we take a block of snow, most of radiation is reflected to me, and really few photons go through the snowpacks. And so these are quite important points. If we want to study the optical properties and the grain size and the albedo of snow, we must keep in mind that even if they are made up of the same material, the way the material is packed and the microstructure is made, it will totally change the optical property. They can reflect everything or absorb and transmit everything. So I put here a nice reading about the optical properties of snow and ice, if you are interested in this topic. As you see, I put just some picture from Antarctica, Greenland, and you see that the type of ice and the optical properties of ice and snow, they are very different. There can be water on the surface, there can be the impurities, and we will see some examples of what kind of impurities can be present on the surface of snow. So let's see some definition, what I mean for albedo. Albedo is the ratio between reflected and incident radiative flux, integrated on wavelengths and view zenith angles. This is quite an important definition because sometimes albedo is misinterpreted and people speak about albedo without having in mind what is actually meant for albedo. Albedo is a double integral, so it's the amount of radiation that is reflected by a surface, normalized by the incident radiation, and calculated for all wavelengths of the solar domain and all possible view angles. So it's quite a complex variable to measure because, for example, from satellite, you can imagine that you have the satellite passing through and it has only one view angle, okay? So from this observation, we must derive the broadband albedo. So the albedo, this definition that I just gave. So there is needed some approximation and some modeling for getting the actual broadband albedo from a single view observation. I hope you understood this because it's quite important to have in mind. Often in the optical remote sensing, we speak about spectral reflectance, and the spectral reflectance is the albedo at each wavelength for a particular view angle. So if you open a Sentinel-2 image, a surface reflectance product, the L2 product, you will have the surface reflectance at one single view angle for different wavelengths. Okay. So when we average the albedo or on a planetary scale, we have the planetary albedo. So the amount of energy that is actually reflected by a planet or moons, they are all different albedo. It's quite important, and I'm going to stress a little bit this point, that albedo regulates the Earth's shortwave radiation. And this is quite relevant because in one slide we will see that the albedo is involved in quite strong feedback of the climate system. A feedback that can be positive or negative. We are mainly interested in positive feedback, so when albedo decrease, how it increase the absorption, and how albedo decrease again, and you will see different example of this, but the feedback can operate also in the reverse. For example, the snowball Earth, it's a result of a negative albedo feedback. Okay, so we are on a course on remote sensing, so I must advise you on the different type of albedo and reflectance, because this plot here is quite. I always come back to this plot when I've been studying during the PhD and the postdoc and what I did afterward, because this is quite. This is from a review paper in RSE, and it basically put the standard of the naming of reflectance, not only for snow and ice, but for all application of remote sensing. So when we speak about, for example, satellite, we often are in the case 8. So we have a diffuse radiation incoming from the sun and the atmosphere, and we can only look on one particular angle. So we are between case 7 and case 8. Case 7 is just directional, it's just a single point of view. Instead, case 8 has a conical observation. Okay, often in the snow modeling and ice modeling community, they speak about the case 9. So the case 9 is the hemispheric incident and hemispheric reflected. So this is very difficult to measure. It's not difficult. You can do it in the field with a cosine receptor that open the reflected flux, and this is the spectral albedo of a surface. So we have many wavelengths, and we are looking at the incident hemispheric and the reflected hemispheric fluxes. So this is quite important to keep in mind when you study papers or they speak about albedo or reflectance of snow and ice. You must keep in mind what they are actually speaking, what kind of measurement they did. So this is very often not clear. As I said, albedo has a strong impact on the Earth system. I will not go much about this. When you have less snow on the surface, you have more absorption and more heat is absorbed by the surface. So you can have a positive radiative forcing, the warming of the surface and the atmosphere as well. So let's have a look on how the snow. In this case, it is a snow on the right, snow spectral albedo plot. Often in the presentation, we will see snow albedo or reflectance. You know how to interpret now the plot that I put here. Snow has a strong reflection in the visible. This is quite trivial, and we know from common experience. And there is a drop of the reflectance or the albedo in the near infrared and the shortwave infrared. And the grain size of snow strongly impact this wavelength. So the larger the grain size, the lower will be the reflectance in the near infrared and the shortwave infrared. This is important. We will see also in the exercise how we can exploit this kind of behavior of snow and also ice for getting parameters. And all these optical properties that you see on the left are coming from the imaginary part of the refractive index of snow and ice, of ice in particular. So if you see, I like this plot very much because it shows that the imaginary part, you see this one, tells us about how the surface is absorbing the radiation at different wavelengths between the visible and the shortwave infrared. And you see these bumps and these ups and downs. They are related to specific features of how the structure of the ice crystal is made. And you see that the black line is ice and the gray line is water. And you see that they are slightly shifted. You see that? And we can exploit this shift to derive how much water there is in surface snow and ice if we have hyperspectral data to cope with. Okay, we will see some examples on this. You see that there are some, I call it absorption features, when we have bumps and, on the imaginary part. And we will see again that, for example, this one is 1030 nanometers absorption feature, and it is the most commonly used for deriving grain size from hyperspectral data. So I put here just a list of snow and ice parameters that we can retrieve from hyperspectral, but also some of them also from multispectral data, such as Sentinel-2 and Sentinel-3. We'll see some example. So snow and ice albedo, the effective grain diameter, or the specific surface area. There is a formula to pass from this quantity to this quantity. And the ice density, or the bubble radius, the liquid water content of the surface ice, and the impurities concentration. So, and the radiative forcing induced by the impurities. So, the presence of small particles in snow and ice has a strong impact on how the spectral reflectance or the spectral albedo bends in the visible wavelengths. And since much of the solar radiation comes in the visible wavelengths, if we have like 5 or to 10% of decrease in the albedo, it will be a game-changing amount for the surface snow and ice, because it will absorb more radiation, and likely if the temperature is at least 0, it will trigger the melt. Okay, so that's something that we are very interested in. At least I am. So how we can model this kind of spectral behavior? There are, I don't know what in the previous lecture you learned about this, but there are this radiative transfer model that allows us to simulate the spectral reflectance or the spectral albedo of snow and ice, changing some parameters. So in the exercise, we will try to simulate some sampled snow properties, and we will try to develop your own retrieval algorithm for getting, for example, the grain size or the impurity concentration. You see here, for example, the impact of solar zenith angle. So if the sun is not at nadir, but is, for example, at 50 degrees, the spectral reflectance of snow will change. And this is quite a difficult thing to cope with, because each model will have to keep in mind the position of the sun. So if we have you have the same snow and you just move the sun on the sky, the reflectance and the albedo of snow will change just because you are changing the position of the sun, because most photons will be bounced off if the sun is very low in the sky, and this is quite common if you are brightened. I don't know how to say, if the sun is very low. Otherwise, if the sun will be very up in the sky, more photons will be transmitted or absorbed by the surface, and the surface will have a lower albedo. So this is something quite important when we are interested in modeling and retrieving parameters. Density has an impact, a lower impact. On snow, grain size, again, you saw this plot as a major impact in the near infrared wavelengths. Dust and snow algae have an impact on the visible wavelengths, and they bend, as I said before, the spectral reflectance in different ways. So we can exploit the absorption features of chlorophyll, for example, or mineral that constitutes the dust to derive the concentration or the radiative forcing. When we speak about ice, this is spectral reflectance of ice and how it is impacted by different parameters like density. In this case, density has a much higher impact. If we go from 600 to 900 kilogram on cubic meter, it will change a lot. As I said before, if we go to the pure ice will absorb and transmit most of the radiation, and less will be reflected. The thickness, the bubble radius, and the algae and dust concentration, again, they bend differently the spectral reflectance. So we have the common idea that snow is quite white and reflective. In fact, snow reflects more than 90% of the radiation back to the sky. And it is considered the most reflecting natural surfaces. Actually, I will try to convince you that snow, but you may know yourself that snow is not as white as we can imagine, because snow can be polluted by different kind of impurities. And most of my work has been done on how this impact the properties of snow, how the snow melts more when it's more dirtier, let's say. And this is the same for ice, because ice can be very dark in color. And also in this case, I spent much time to understand what are the optical properties and what are the consequences of this darkening, let's say, of ice and snow as well, and what are the constituents. So, what are the impurities? As I said, snow and ice are involved in the albedo feedback. You know this again by experience. If you have fresh snow, the albedo will be less than 1, so 90% of reflection. As the snow starts to melt, the albedo will go like 0.6, 0.5, and when you have the bare eyes exposed to radiation, you have as low albedo as 0.2 and 0.1, and this is quite a big thing for the surface, because it is absorbing 80 to 90% of the incident radiation in the period where the incident radiation is stronger, okay, during the summer season, okay. So the albedo feedback is mediated, let's say, by the grain size, as I said before. I don't know if you can read, okay. No, not very much. Fresh snow has a high albedo, and old snow is like 70% of reflection. And there is this grain size feedback also with contaminated snow. So if we put some soot or some carbon particles, absorbing carbon particles on the snow, they will increase the absorption, and this increase in absorption will increase the grain size of snow. And the grain size, if the grain size is getting larger, more radiation is absorbed again. So there is this albedo feedback that is usually studied at the end of the melting season, when all the impurities are at the surface. So the melting feedback is at this stronger moment, let's say. In polar region, we have different snow and ice albedo feedback. For sure, the fragmentation of sea ice, and now they expose the ocean, which has a very low albedo to the surface. Or in Greenland, for example, we will see some examples about this. We have some portion of the Greenland ice sheet that is covered with very dark ice, and in fact, this area in southwest Greenland is called the dark zone. I don't know if you ever heard about this. People struggle to understand what this darkening what was causing this darkening. And the spoiler is that there is a lot of life on Greenland ice sheet. There are algae thriving at the surface, and cryoconite, which is a mixture of sediment of organic and mineral. And these are coming likely from below, some from Pleistocene ice, very dark ice, and with this strong melting they resurface, and they let the surface melt very fast. Okay, by using Sentinel-2 images, we can actually track this kind of feedback mechanism, also from a visual perspective. In the exercise, we will see something about this. So these are a loop of Sentinel-2 images of the Aletsch Glacier, and you see how the change of the surface is happening. So we have a blanket of clean snow, and the snow starts to get dirtier and redder, let's say, and as the snow depletes and the snow line recede, we have the exposure of the dark ice, which you can see it's like asphalt. So the albedo of this we will calculate, it will be like 0.2, 0.1, so it will be quite relevant for, in particular for the modeling community, to take into account the albedo of ice, because there is not much exchange at the moment with the modeling community. They use 0.35 as a bare ice albedo in the models, and they don't assimilate from satellite. So one step further will be to assimilate directly the Sentinel-2 albedo to get a better tune of the melting and the surface mass balance. In West Greenland, we have a similar situation when the melting starts. We have this formation of the supraglacial lake, and with Sentinel-2 we can monitor them very nicely because of the higher temporal resolution of Sentinel-2 in the Arctic. Unfortunately, it's not the same for Antarctic, where the orbits are not overlapping as nicely. This picture here, I show some sample spectral albedo of snow, bright ice, and dirty ice, as seen from APEX. APEX is an airborne spectral imager from Zurich University. And these here are the Sentinel-2, Landsat 8, and Landsat 5 and 7 spectral bands. So we will see also other kind of representation, but I think it's useful for understanding that when we look at Sentinel-2 images, we see only on through specific windows of the bands. So the whole story is represented. So, for example, this big absorption feature I was speaking about before is the 1030 nanometer. It's completely overlooked by this multispectral sensor. So if we want to accurately estimate the grain size, we will need some spectrometer with bands here, for example. But we will see that we can find out how to exploit the impact of grain size also in the other bands. Okay. So here I calculated the albedo by using a sample narrowband to broadband conversion proposed in this paper that is actually based on Liang broadband conversion for Landsat. And in this case, we will use, for example, band 3 and band 8 or other bands in this other formulation of Sentinel-2 to get a broadband albedo. So basically, we are putting some coefficient in front of the reflectance of snow and ice, and we can, in this way, calculate the broadband albedo. You will do it yourself in the exercise. So you see that the snow here has a very high albedo, and as we go down to the glacier tongue, the albedo is very, very low. It's 0.2 or 0.1. Okay, from Sentinel-3, we will see in a moment, we have the possibility to derive also the grain size or the specific surface area. The specific surface area is reflecting basically the structure of the surface snow. Okay, not only the diameter of an imaginary sphere. So for passing from the radius of the optical radius of a snow crystal, we will know we will have to know the density of ice, and we can pass from one to the other. This is an example that we did some years ago with Alexander on Sentinel-3, where we use automatic field spectroscopy measurement as a validation for SSA retrieval from Sentinel-3. You see that the SSA is quite it's not very clearly changing through the season. If you look at to an albedo series, albedo will be higher at the beginning and during the accumulation period, and then when the melting starts, albedo will get down. Instead, the grain size or SSA is changing very fastly, because you can have just a snowfall, and the structure will change, so you have this ups and downs. But at least it looks like Sentinel-3 is doing a good job, at least to get the values right. Here you can see again the a sample spectrum from this automatic spectrometer overlapped with Sentinel-3 ALSI reflectance data. So you can see that they quite nicely reflect the shape of the spectral albedo, but with a resolution of 300 meters. So if we want to look deeper in a glacier, we will need like more like 30-meter resolution. Otherwise, we will just have to look at very wide areas, such as in Greenland and Antarctica. Here again, I show some simulation of the impact of mineral dust and snow grain size on the spectral albedo of snow. You see again this drop here due to the grain size, and this drop here due to the mineral dust. So sometimes what we have to do is to find a good way to get the dust concentration or an index like the NDVI for vegetation, for getting parameters of the surface. So sometimes we use complicated models to retrieve the surface, and sometimes we just use spectral ratios. But spectral ratios, they are simple, but they work. So, we will try some example. In this case, I show an event of Saharan dust through snow on the snow surface, and how they change the surface. So what happens here, as this is our measured reflectance, and how they change in the visible wavelength. So easily, if we see that the higher is the concentration, the stronger is the bending in the visible wavelengths, we can take in this case we use the Landsat 8 a Landsat 8 scene for getting not the concentration, but actually the radiative impact, because the concentration it's quite difficult to get. But for getting the concentration, we often apply this kind of variable selection approach. So we use the radiative transfer model to simulate different kind of snow, and we calculate all possible bend ratios or normalized difference like NDVI. In this case was a normalized difference, and we look for hotspot of concentration between the wavelengths. So in this case, in the left plot here, we have this simulation with SNICAR and the ASD. ASD is a field spectrometer. So we found out that this area, if we calculate the normalized index between 600 and 500 nanometer, we will have a good correlation with the measured concentration of snow in the lower plot and the simulated concentration of snow in the upper plot. So other approaches are more complicated. They use the ART theory, the asymmetric radiative theory, transfer theory from Alex Kokanowski, and they again these are data from a field spectroscopy that we have, spectrometer that we have in the Alps, and in the dotted line is the theory, so the simulation, and the red line is the measurements. So and the simulation has been made only by looking at these three wavelengths here. So in this case, for example, we don't have the reflectance in where the grain size is having the impact, so we are using the last possible wavelengths in the near infrared. Okay, so this modeling brought us to try to simulate how the snow is depleted earlier during the season because of the presence of impurities at the surface. In this case, we use the Crocus numerical model to simulate the evolution of the snow by including or excluding the presence of impurities at the surface, and we calculated up to 38 days of earlier snow melt. So this means that when you have this, these are the yellow line and are the concentration of dust, and the red dots as well. So you have the deposition of dust here, here, and here, and at the end of the season they resurface at the same moment, and so at the concentration at the surface is very high, and the melting albedo feedback is very, very strong. So and this is so strong to bend the snow depth curve. Other application of in this sense is from Sentinel-2. These colleagues made use of Sentinel-2 images. They were so lucky to have Sentinel-2 images just after a big saran dust event in the Caucasus, so they managed to invert their model to calculate directly the concentration of dust at the surface, and they feed it directly into the Crocus model to estimate how the melting was modulated by this event. From Sentinel-3, as I said, we have to look at wider areas, and we did some tests in Greenland, for example, to estimate the snow grain diameter and the broadband albedo. And the model that we use here is working quite good for snow, but it's not very good for ice, because, as I said, snow and ice, they have very different optical properties. So this was a first guess of the grain size and albedo derived from Sentinel-3 over the whole Greenland ice sheet. And as you see, the albedo also has a very dynamic changing through the season, because it gets darker it gets lower during the melting season. We did the test also over the whole alpine chain with Sentinel-3 for albedo and grain size as well. And we compared these two approaches based on Painter and others and Kokanowski theory. So they gave quite different results, but at least is a demonstration that this data can be used to retrieve snow and albedo grain size, and they correlate quite nicely with ground measurements. And you can imagine that the ground measurements of grain size are quite complex, because there are many different approaches and methods to measure the grain size of snow. So it's quite tricky to get validation from this side, because often we retrieve parameter, but we need also to have the ground validation of the parameter that we are interested. Otherwise, it will be like putting paint on the wall, and there will be a very nice pattern, but there are no scientific interest. Speaking about Greenland, what has been done in the past also is to calculate the albedo anomaly through time over the old Greenland ice sheet, and in particular in this area, which is the dark zone I was speaking before, which has very low albedo. So the anomaly it is negative, so it means that it's getting darker through time between 2000 and 2009, for example, this old study from Modis. And we can also calculate the albedo at different wavelengths. So if we are interested only in the visible part of the albedo, we can use only those data, or the near part or the shortwave infrared part. So if we know, for example, that the sphere and the near are influenced by the grain size, if we see a negative trend here, it means that the grain size is getting larger through time. But if the visible anomaly is getting darker more strongly, it means that the grain size only cannot explain the whole variability of the trends. So the conclusion here of this study was that there is increasing concentration of impurities at the surface in the last 20 years that needs to be studied to understand what are the cause and the consequences of this darkening of the Greenland ice sheet. Going back to the Alps, the picture that we have in mind is this one. So the albedo is higher during the accumulation period, and the albedo goes down. We are speaking of glacier at the moment, so we are looking at pixel on the Aletsch Glacier again. We see that the albedo goes down and reach a minimum, and then start to grow again. And when during October, November, the albedo is high again. So in the study that we did a couple of years ago, we tried to model this kind of drops and increase by using a sample analogy with the vegetation phenology. So a lot of people studied vegetation phenology to understand the onset, the greening onset, so the start of the season, and other metrics related to the growth of vegetation at the surface. In this case, we have a reverse situation where we have the albedo that drops and goes up again. So we put this threshold. So we said when albedo is lower than 0.5, we are quite confident that the glacier ice is exposed to radiation. So we call this point in time the start of the ablation season. And when we have again this threshold passed, we have the end of the ablation season. So in this way, we also calculated the minimum albedo of the season. So if we look through time and space, this kind of glaciophenological metrics, we can estimate if glaciers, at least in the Alps, are getting darker or the ablation season is getting longer by using MODIS data. And in fact, we found out that we have some trends at the surface. In particular, the minimum of the albedo is getting lower, so we have some darkening at the surface, and so we wanted to look at where this darkening was located. So it was the ablation area that was getting darker, or the accumulation area. So we found out that this is quite comprehensible, that the darkening occur mostly at the equilibrium line. So the accumulation area is getting smaller and the ablation area is getting larger, at least at the MODIS scale. So we can estimate this kind of properties on the whole alpine chain. Another thing that we did in this study is try to link the minimum of the albedo, the early albedo, with the glacier mass balance, because as the glacier gets darker, it's also losing more mass. So we found out that there is a quite nice correlation between the minimum albedo and the mass balance of all glacier from the WGMS system. So this allows us to say, okay, for area where we can't go there and there is no monitored glacier, we can at least estimate the surface mass balance by inverting this model. That has been parameterized in the Alps, but probably the coefficients are different for different kind of location. So let me check the timing. So I'm quite late. What drives the albedo change? So we went through to understand what causes the darkening. As I say, I mentioned the cryoconite sediment again. Here we made use of Hyperion. Hyperion is an hyperspectral sensor from NASA that has been decommissioned now, so it's not working anymore. And we tried to exploit the reflectance read by Hyperion over the Morteratsch Glacier to try to estimate parameters. I'm going a little bit faster in this on this point. What I was interested in this case is try to understand how the albedo and other impurity index are influenced by the grain size, for example. So I made use of the Snicker model again to simulate different imaginary snow with a concentration of dust and a particular grain size, and I was trying to understand which index is less influenced by the grain size, because I was interested in the concentration. So here you have the SDI, is the snow darkening index, that is calculated by normalizing the difference of red wavelengths and green wavelengths normalized by the sum. And the impurity index is calculated as a ratio of logarithm between the green wavelengths and the near wavelengths. So you will calculate this index yourselves during the exercise, and you will see what are they reflecting, what what they are correlated with. So in this case, I came up to the conclusion that the impurity index is not correlated with the snow grain size. You see there is no variability for a particular concentration of mineral dust or black carbon. So if we want the concentration, we will use the impurity index. Otherwise, if we want the radiative impact, we will use the SDI. And this is the albedo visible calculated as an integral of the visible wavelengths of the reflectance. Okay. By combining all wavelengths available from Hyperion. And these are the results from that study. We managed to estimate these properties, and we combined all these three indexes in this representation, RGB representation, to understand where in the glacier the index were more important, let's say. So we came up to the conclusion that, again, this area between the accumulation and the ablation area was mostly affected by SDI. So probably there were dust on the surface, since SDI is correlated with dust, and the impurity index is more effective, like in the ablation where we have bare ice. At the Mortarash Glacier, we have also some white ice at the surface, in the ablation area. So there is some yellow hues also here. So we went deeper to understand what causing the darkening of the Mortarash Glacier in particular, and we found out that the ice was getting purple in some years, and we took some samples and analyzed the samples, and we measured the spectral reflectance of the surface, and we found out that the higher is the concentration of this glacier algae, the lower is the reflectance of ice. And so, again, here you see this shaded band on the background of this plot is the Sentinel-2 bands. So we were interested in understanding which Sentinel-2 bands were mostly correlated with the concentration of glacier algae in order to be able to estimate them from satellite. And we found out that this B6 and B4, if we calculate the ratio between these two bands, you get a good guess of the concentration of glacier algae. And this is quite curious that the same algae that we found on the Mortarash Glacier, they are causing the dark zone in Greenland. So they're kind of this similar situation of bare ice exposed for a long period during the summer season. And so this kind of organism, they find the good environment, the optimal environment to grow and reproduce. And the throwback of their growth is they get the ice darker and it melts faster, and more supraglacial lakes are formed in Greenland in particular. The new generation of satellite data will be hyperspectral rather than multispectral. So they will have many bands like Hyperion, and this Prisma satellite mission is promoted by the Italian Space Agency. We are working quite heavily on this data in different projects, so I will show you some examples. There will be useful for the future satellite mission. So Prisma is an imaging spectroscopy with more than 200 bands in the visible near-infrared and shortwave infrared, and the spectral resolution is lower than 12 nanometers, so we can resolve quite nicely the spectral features of snow and ice, at least better than multispectral mission. What we did is try to calibrate and validate this kind of observation by setting up experiment at the field. So we put an automatic spectrometer in a quite wide field in Tornion in the Aosta Valley, and we did some campaign in Plateau Rosa Cervina, where there is a very flat area. We'll see the picture in a moment. And also in Antarctica, we went to a very flat area with low variability on the optical properties of snow. And we tasked acquisition from Prisma on the same day to have the match-up between the reflectance measured at the field and measured by the satellite. These are results from the Tornion site. and these are results from Platorosa. Platorosa it's a quite perfect place because it's very easily reachable by the cableway, and we can go in this area mainly. In this area, which is quite flat, to measure the spectral reflectance in the field and to propagate the signal to the top of the atmosphere to see if the radiance at the top of the atmosphere is observed in a good way by a prisma, and also to have a match-up between the top of surface reflectance, so to understand if the atmospheric correction of prisma is working fine in a quite homogeneous area. These are some results from radiance. I hope that you have in mind what is the difference between radiance and reflectance, so I give it for granted. Radiance at the top of the atmosphere, so without any atmospheric correction, is on the left plot, and the right plot is the spectral reflectance at the top of the so at the bottom of this atmosphere, top of surface. So we see if the atmospheric correction worked fine. There is a trick here, because Platorosa is so high, is 3,500 meters above sea level, so the most of the polluted atmosphere that we have lower is not taken into account, so I'm not very surprised that is working fine. But what I was happy about is that the bending of the reflectance here, that is due to the mineral dust impact, is nicely resolved both by prisma, and the blue point here are Sentinel-2, and the red is prisma, and the black is the spectral evolution. Spectral evolution is another spectrometer that we use in the field for getting this kind of measurement. These are results from Antarctica, quite similar. And again, if we look at prisma spectra, for example, on the Aletsch Glacier, we can see that the absorption feature in 1030 nanometer is nicely resolved, so we can exploit it for estimating not only the grain size but other parameters that you will see in a minute by using sneaker simulation. So these are a sample representation of the RGB image of prisma, and NDGSI, which is a normalized index between these two wavelengths, and the SDI again. And we see that the grain size increases as we go lower on the glacier, and the SDI is higher again in the transition between the accumulation and the ablation season, where the impurities get concentrated by the melting itself. Okay, so I was speaking about the difference between the imaginary part of the refractive index of ice and water. So we exploit this shift by building a model to retrieve the liquid water content in snow. So these are simulation with sneaker of snow with 0% of liquid water content and 20% of liquid water content. And what we see here that we have a shift of this absorption feature left on the left. So we try to understand if this shift is also displayed in the spectroscopy data that we collect in the field, and if Prisma is able to see this as well. So this is how we built the model. So we calculated the semi-area normalized by the depth of this absorption feature. I will go fast on this, but what we were interested in is to not be influenced by the grain size. The grain size is the integral of the whole absorption feature, but we are interested only in the leftward shift. So we normalize for the depth of this absorption feature. So we went to the several field campaign on this to understand if, when we measured with sensor the liquid water content, the shift was displayed also in the spectroscopy data, and this was true. And so we built a model to apply to Prisma satellite images, this retrieval scheme, and so we classified this sample image from Prisma with the liquid water content from 0 to more than 15%. So this is quite interesting for us because it is a quite a good application of the hyperspectral data. This cannot be done with multispectral data. Other thing that we did is to use this Prisma data for getting the effective grain diameter, so the grain size and the albedo of snow in the same area that we use for validation in Antarctica. And we are now working again to the validation of this estimate with the field measurement of the grain size. Okay, I'm getting to the end of the presentation. So I just put also this couple of slides about the something that we did in Antarctica by using Sentinel-2 images and field spectroscopy data. Sometimes in Antarctica you have this blue ice fields. I don't know if you ever bumped in this, but the blue ice has a very low albedo. We observed this transition of blue to white ice during the melting season. So, as you saw, I at least was expecting that the albedo was going down through to the melting season. So I was going there with the helicopter to say I want to catch the moment where the darkening is at its best. But what happened that we went in the field and everything was white. So we thought that it was a snowfall, but there was no snowfall in the area. What we learned about this is that sometimes the ice, when it's get to the melting period, get this porous ice layer at the surface that is called the weathering crust. And the weathering crust is so reflective that is putting the albedo up again, so it's acting like a reverse albedo feedback. So we were expecting to get a darker ice in Antarctica during the melting season, since there are also impurities in this area. We were interested in this in particular. So we learned that in particular condition of humidity of the air and radiation and cloud cover, the ice can change at the surface and get this white ice displayed. And if we calculate the radiative forcing of this white ice, it's all negative. So it's getting the surface cooler and not warmer as we are used in Greenland and in the Alps. This is quite, at least, interesting application I put here to show how actually albedo can be used or informative for monitoring the surface of glaciers. We did similar thing also in Greenland, where the ice is like this, so it's very dark in color, and we have ice streams at the surface. So in this case, we were interested in estimating the ice grains, the snow grains, and I mentioned the liquid water content, not in the same way that we did in the other study, and the glacier algae concentration. In this study, we actually use a statistical model to invert the reflectance directly into the surface parameter. We didn't have any validation of this, so we looked at past studies from Joe Cook, and we just put the concentration together to see, let's say, if we at least get a concentration that is measured in the past, and this was the case. So all this data needs to be validated. So last year we did a campaign in Kanak ice cap in contemporary to satellite acquisition to see if the concentration that we estimate from the satellites is similar to what we measure in the field. So we are allowed to use this model to track the evolution and the change of the surface of ice through time and space. This is what we are doing in the Kanak ice cap in northwest Greenland. So I come to my conclusion of this 1 hour of, I will say, it's a storm of application of reflectance data to snow and ice. So I hope that you at least understood and learned something new about this application. We saw that snow and ice reflectance can be used to retrieve a series of parameters that we can be interested in just for the retrieval, or to retrieve this parameter and put in some models to assimilate and simulate and improve the simulation against observation. I show you some Sentinel-2 and Sentinel-3 application that we did in the past for snow albedo and grain size, and we learned what can induce a darkening at the surface of snow and ice in different locations of the world. And I put some word also on the future satellite that will be hyperspectral, like CHIME from ESA and SPG from NASA. And since Prisma and Nmap, they don't acquire, I forgot to say this, they don't acquire continuously at the surface. They only provide on-demand acquisition. So I asked the space agency to acquire an image in the particular place, so I can do I can play with the data. But in the future, this CHIME and SBG and the Prisma second generation, there will be more like Sentinel-2 in terms of temporal resolution. And also spatial resolution, it will be more like 10 meters and less like 30 meters. So we must be aware of what we can do with this kind of data when they will be available in few years. So thank you. I acknowledge the project that supported it. I don't know if you have a question about something, or I can leave the stage to Carlo for his.
This weathering process that you have been talking about, do you know how exactly it forms, or is there any complication on this?
Yes, there are more evidence in Greenland, in the northern hemisphere, rather than in Antarctica. The formation is related again to the presence of impurities, because they create this porous layer. I put this picture here because when you have the formation of this weathering crust, you have a porous layer. So it's not completely clear, and it's different from Greenland. And sometimes we have weathering crust also on the Alps. In the image that I put for the exercise, there is some area of the Gorner Glacier that appears very white, and likely that is the weathering crust. So the actual physical process that leads to the formation of the weathering crust is not completely clear, and it changes from the location. In general, is related to the structure of the ice grain that tends to grow and include more air in the surface. So you go from a solid ice, which is very, very dark in color, very, very dark, to this highly reflective surface. Okay.
You said from size, Sentinel-3 has problems with like the ice amplitude retrievals.
Yes.
What's that amplitude to?
Yeah. All right. In that case, the model that we use, the Kokanowski. Sorry, I speak clear. The Kokanowski model is built for reflective surfaces. So when he reads reflectance like lower than 0.5, 0.4, the model is not able to invert and get to the properties of the surface. This has been resolved in a Niklas Bonn approach, the optimal estimation approach. This is the in this case, he managed to retrieve also properties of glacier ice, not only snow. But for Sentinel-3, at the moment, the Alexander model is not able to get the properties of ice. He's working on this with the data that I provided, actually. But at the moment, this size, snow and ice pre-operational algorithm is not working fine. You can there is on GitHub. So if you are interested in this and you want to play, you can actually use this model to have an estimate. I remember during the review of this paper, we were struggling with this area that at the end, we just masked as bare ice since the paper was on snow. So there will be hopefully another one to get the ice properties. Instead, for example, if you calculate with the narrowband to broadband albedo conversion from Nageli, you can have a good estimate of the surface broadband albedo, because we measured, again, I didn't show the results from the Zeebrugge glacier, and we tried to match up those two. So I'm quite confident that that broadband conversion is okay, but what I did not measure it is the anisotropy of snow and ice, which I'm not considering here because it will be a mess. So this broadband conversion does not take into account this. Okay, if there are no more questions, I leave the stage to Carlo.
Grazie.
Allora vai, perché la spina è alta da sotto. Aspetta, magari viene la tizia a darci una mano. Comunque devi metterla qua sotto. Aspetta, se no guarda, ti do la mia perché la mia è rimasta attaccata. Puoi lavorare qua oppure la tiva me l'ha caricata su questa dove ci sono tutte quante.
Okay, thank you. But I think it's good to have a little bit of break. Okay, if you are here, I think we can start. Sorry for my voice, but I have a little bit of cold. I don't know, this weather is a little bit crazy, seems. We had summer in Italy, but now it's full of snow, like here. And speaking about snow, we are going to see something related to the snow cover fraction mapping from optical data. I think you already see something in the previous lecture that you had, but I think it's good to go a little bit over again and see some definition and a little bit of introduction of what the fractional snow cover area is. And then we will see state-of-the-art methods for doing this at different level of complexity. We will see how they are dealing with the spectral variability in real scenarios. And finally, a little bit what I want to try to communicate and give you is a method, a bag, let's say, of tools that allow you to perform something that is a little bit more different than the state of the art and is related to the nonlinear unmixing. And then, of course, we will see some example if this is working or not. Okay, so let's start. I try to speak here, close to the microphone. The snow cover area actually has many names around the literature, so you can call it snow cover area, snow cover, snow stand. Everything is always the same and is refer to the fact that we are measuring the square meter that are covered by snow. Normally, we are doing this confined in a given catchment, so for a more, let's say, convenient way to express it, we are just taking the ratio between the snow area and the total area of our catchment. One or at least a couple of nice properties of snow cover fraction, if I'm providing you this number that is expressed in percentage, is actually, it is not differentiated between a very deep or very shallow snowpack, but for example, if we have a catchment here, 100% fully snow cover, you don't know if it is a lot of snow or a very shallow cover of snow. And then the second nice properties of the snow cover fraction is that actually giving that number, you cannot really reconstruct where the snow cover actually is inside our catchment, except of course for trivial cases. Okay, but say that, let's go a little bit deeper and try to understand how we can measure this normalized area. And since we are using digital images, what we are doing is actually counting the number of pixels that are covered by snow, and we divide it by the total number of pixels. Of course, this is depending on the resolution of the images that we are using, and if you are not, let's say, fully adhere to the Nyquist-Shannon sampling theorem, what is happening is that we have a distortion. So the Nyquist-Shannon theorem is, for the one that doesn't know it, is just a rule that is saying when we can, how we can sample a continuous signal. So, for example, in the case of the snow, we have a frequency that is the maximum frequency, so the maximum change that we have in space. So we can assume that the snow is actually fully % covering a resolution cell of about 1 meter by 1 meter. And so we cannot have fractional inside this cell. And if we are sampling with a frequency that is lower than this frequency, so if we are sampling with a resolution cell that is 10, 20, 500, 1 kilometers, actually we are not respecting the Nyquist theorem, and what is happening is that we cannot really calculate with this formula the snow cover fraction. What is quite unfortunate is that actually most of the satellite, and especially the ones that are providing data in a free manner, like all the Sentinel mission, from example, from ESA, actually are providing images with a resolution that is bigger than this 1 meter that will allow us to respect the Nyquist-Shannon theorem and completely using this formula. So what we have to do is actually, before calculating the snow cover fraction of all the entire catchment, is actually calculating the snow cover fraction of our pixel, because it will be very likely that inside this pixel there is a fraction of snow and a fraction of bare soil. So how we are going to do this? You have to imagine that we can have 3 different pixels, and we have only, let's say, one information. So in the lecture before, in the many examples that Biagio was providing us, actually we know that we can have actually one information to solve this. That is the spectral information. In fact, we know that a pure snow pixel has this very characteristic signal or signature, we can call it, is the reflectance. As Biagio was telling us. And what is happening as soon as this pure, let's say, spectral feature is mixing with another one that is coming from, for example, bare soil, what is happening is that our signature is evolving, is changing until to the point that is arriving to the other signature of bare soil in this case. So this is a mixing. So we are just mixing spectral feature. And what we think is possible to do, let's say, this is our hypothesis, is that there is a function that is connecting the signature that we are observing with the snow cover fraction. And we will see later how we can, with different level of hypothesis, calculate this function. One thing that is always important to remember is that, okay, it is true, normally we are dealing with images that have a resolution that is higher than 1 meter, but sometimes we are very lucky and we may have an image with low resolution together with an image with very high resolution. Just imagine to have a planet or a world view or whatever commercial satellite images that we can acquire. In that case, what we can do is again using it first of all as a reference and calculating the Snow cover fraction, just counting the number of pixels. And so this is very important, especially for trying to having methods, automatic methods that are trying to calculate the Snow cover fraction. So as we saw before, Biagio was saying that many times is much more convenient instead of using all the information coming from the spectral reflectance, taking only spectral indexes. This is convenient, but sometimes for the multispectral images is actually the only way. So if, for example, here we are calculating the NDSI index, that is the normalized difference between the visible and the shortwave radiation, and I think you were already introduced with this concept, you can imagine that the NDSI in this case for 100% Snow cover fraction is high and is decreasing as soon as we are moving toward the bare soil. So if we have a reference, like in this case, we can try to have a relationship, try to establish this relationship between the Snow cover fraction and the NDSI, and then having the so-called regression. So mainly I want to show you two of the most used, or the ones that are relevant in this course, regression that are used. The first one was introduced in 2000 from Salomonson and Appel, and actually is a very simple linear regression that is connecting the NDSI with the Snow cover fraction. They were trying a lot of coefficient for this linear regression, but in the end it seems that this one are the one that produced the better result. But of course, as you can see, also in this very simple example that was provided in the original paper, there is a scatter of this point, so the relation is not always good. So that's also why they were trying to think and to find the best coefficient. Anyway, we will see during the exercise that we have later in the practical part of this course how we can also modify this and which result we can get. But beside the linear regression, that is the easiest one, the one that can be computed very, very quickly, there was also proposed, instead of using MODIS, like in the Salomonson case, but using the Sentinel-2 images, and comparing with Pleiades images, also at high resolution, was tried to say, okay, maybe the linear regression is not that good, let's try to do something that is non-linear, and here was proposed hyperbolic tangent. As you can see here from this scatter plot, at least also in my view, it's not necessary that this is getting better result than this one. But still, is another way to compute it. It was done for Sentinel-2 images, and we will see later how it's performing also in practice. One very interesting thing I want to mention here about this method is that, you know, before start to think that basically all the pixels coming from all the most common satellite mission like Landsat, MODIS, Sentinel, Sentinel-2, Sentinel-3, and so on. There was only the necessity, or at that time, it was only provide a binary information. So what was done in the so-called binary algorithms that were proposed was just to threshold the NDSI at 0.4. I think maybe some of you are familiar with this threshold. You can also apply when you want to have a dirty and quick job done. But what is interesting to notice here is that if you are thresholding the NDSI at this 0.4, actually what you get is something around 50%. And this 50% actually is not just a random number that we want to get in a case we are providing binary information, but is, from a statistical point of view, a very nice thing to do, because if you have a lot of pixels, and you are thresholding at 50%, you have a statistic. In a statistic way, you can say that sometimes you are overestimating, and on other cases you are underestimating. And this, if you have a lot of sample, is compensating. So in the end, if you are looking at the metrics, also this very simple and very dirty, very quick classification method are not performing so bad. Okay. But let's move a little bit more on something more complicated. Biagio was showing us all this spectral signature, and how they were evolving. So using only a spectral index is something that is a little bit, reducing all this information to only one value. Instead, one can think to use the entire information. And here is coming the linear unmixing that I try to explain you here in the easiest way as possible. But before doing this, I think it's important to say that we need to have some hypothesis for the case this linear unmixing is working. So first of all, inside our resolution cell, we need to have only a small number of distinct materials. So we cannot have 100 material inside the resolution cell and, let's say, try to see how is the fraction of all this material using the spectral unmixing. Then the second thing is that, and this is the most important, the photons that are reflected from this cell actually are in proportion with the area of each of the components. So if you have a majority of snow in this resolution cell, that means that the reflectance or the majority of the photons are coming from this part of the terrain covered by snow. And of course, it's not just a proportion, but should be a linear proportion. And then the last important hypothesis is that we know, of course, all the pure components that are involved. So if here we have, for example, in the snow-free part, we have grass, rock, and whatever, we need to know everything of them. Otherwise, the linear unmixing is not working. So just a little bit of naming convention. So the pure and distinct components are called n-members, and the fraction in which they appear in the pixel is called abundance. And what is actually happening is that our reflectance that we are observing, that is related to this pixel in this case, is actually equal to the abundance of the first component, so in this case of the snow, which has an n-member spectral signature that we know now very well, plus the abundance of the second component, in this case of the rock. Okay, quite easy. So how we can solve something like this in a mathematical point of view? So first of all, if you are bright in the mathematics here, you can understand that what I'm saying is that the observed reflectance is actually equal to a sum of all the m-member that I have inside the resolution cell multiplied by the abundance plus basically a noise that can be any additive Gaussian noise. And so in matrix form is something like this. This actually system of equation has to be subjected to two constraints. The first constraint is that our abundance is between 0 and 100%, so between 0 and 1, and the sum of all the abundance is equal to 1. Okay, at this point, maybe also to try to, let's say, entering into what is also the purpose of this lecture, a system with, let's say, a number of equations that is bigger than the number of variables, how many solutions has in general? You have more equations than variables. In general. So, or better, let's start, if you want, from the other case. If you have more variable than equation, you have infinite solution. This is the other case, so you have 0 solution in general. So it cannot be actually solved, but what we can do, of course, starting from the unconstrained solution, so don't considering this constraint at this point, is actually calculating is computing first of all the normal equation from which we can calculate the pseudo inverse, and from this pseudo inverse actually we can estimate this alpha hat here. That if you are taking out your notes from the algebra and geometry lecture that you have at the university, is exactly the same like minimizing this L2 norm. So basically what you are doing, you are taking your observation, you are considering all the possible mixing that you can have for that case, you are square it, and you are taking the one that is giving this the minimum of this difference. So it is what we call the least square solution. But of course, this is only true if the number of bands are bigger than the n member. And actually, this matrix of the n members is actually full rank. So that means we have a number of equations that is bigger than the number of variables. But this is only a part of what we are doing here, because normally this, or better, this is only the solution of the unconstrained problem, to which we have to add the constraint that we have here. So from a very, let's say, sweet mathematical point of view, there is, yes, let's say, only partially possible to solve in a closed form this problem with the Lagrange multipliers that actually we will see later. Especially for the constraint of the fact that the sum of the abundance is equal to 1. But let's say there is no closed solution for alpha that is strictly non-negative. So what is normally be done is actually ending this problem to the numerical mathematicians that are very happy to solve this kind of problem that are called quadratic optimization problem. And so you are just taking the one that is minimizing this, basically this norm in L2. So before many questions that maybe you can have, I want just to tell you why I'm telling this to you, and I try to explain this, is that normally when you have a linear mixing problem, everybody is thinking about the minimization of this stuff here. But actually, this is coming because you have a real problem that has to be with this, let's say, constraint here, and has to be with a number of bands that is bigger than the number of n member, and E has to be full rank. So basically, if you don't have this problem, but you still want to resolve in this way your problem, you are basically not solving a linear mixing, but you are solving something else and you are just minimizing this. So be very, very, very careful. And we will see maybe also during the practical exercise what I mean with this. But just maybe, since I see some strange faces here, maybe let's say I have this problem here. How you would solve this, given this? I mean, you know this, the reflectance, you know the member 1 and member 2, and you are missing alpha 1 and alpha 2. And you have just to find out the solution that is minimizing the difference between these two terms here. I think I was in the same situation when I was a student, but actually the solution is very easy. You can use a brute force approach, so basically the very easiest without talking with the numerical mathematician is just taking alpha 1 to 0.1, alpha 2 0.9, calculate, multiply by the member 1, multiply by the member 2, take the difference between this and what I just calculated, square it, and making the sum for all the bands. And this is my first number. Then, second number, I take alpha 2, 0.2, alpha 1, 0.8, so the sum is equal to 1. Make the calculation, make the sum, and this I have the second, and I just taking the one that is the minimum. So this is my alpha 1 and alpha 2. Of course, if you give this to mathematicians, they are just putting in this form. That is a quadratic optimization problem. There are techniques to go through this, also considering the constraint, and they are quite fast. Okay, so now let's move. I hope you understand this. It was very difficult for me when I was young, but I hope you were able to get this. Then let's move and do a little bit another step forward and try to understand what is happening actually in the reality. So now we have two methods, two state-of-the-art methods. One that is very easy and is NDSI regression. The second one a little bit more difficult, that involving the knowledge about the members and the reflectants that are observing. But in reality, what is happening? It is happening that actually the reflectant I observing, as Biagio was also showing you, is actually, let's say, that there are some effects that we are going through right now that are changing the spectral signature that I'm expecting. The first one is the atmospheric interference. So you can understand that the best condition is to having the sun and then a direct reflectant to our satellite. But of course, you can have, of course, a reflectant from here I depict like clouds, but you can imagine like atmospheric component like water vapor or whatever that is actually reflecting the sunlight toward our satellite. Then this vapor can also reflect this toward the ground, and then from the ground toward our satellite. And then you can also imagine that you have one part that is reflecting to a very close pixel that I'm considering, that is reflecting this stuff on the atmosphere, then is reflecting back to the ground, and then is arriving to our satellite. So basically what we are measuring, layer reflectance, is something that we need to correct. And compensating this effect is generally quite difficult, and normally they are providing with the so-called L2 products that you can, for example, download from the ESA website directly, if you want. But you have to understand that if for some reason you have a bad specification of this kind of model and you try to correct it, you are propagating an error inside your reflectance. But this is not the only source of error, or let's say of possible alteration of the reflectance that we have. The second one that Biagio was already partially saying is the illumination condition. So basically, especially in the mountain terrain, we can have that our cell is not completely flat, it's just on a very steep slope, for example. And from this slope, you can, let's say, without entering into the detail, and we will see later some practical example, having two distinct effects. The first one is very easy, is you have shadow. So basically, there is no sunlight, no direct sunlight on your pixel. And the second one is actually an angle that is forming from the sun to our satellite, that in the case, or in the worst case, can be really similar to the case in which you have a sun tilt, like when you are looking at the lakes or the ocean or whatever, and the sun is very low, and you get exactly a lot of reflection into your eyes. Also, this effect might be compensated. Also, this effect can be compensated by the so-called L2 products. But again, if you are not providing all the information for doing this, you are making maybe even worse this problem. And then the third one that I think you already imagine, and this is actually very important, is the intrinsic variation of all the pure ground components. So Biagio was showing you that by changing snow grain size, if you have impurity inside the water, if you have liquid water content and whatever, the spectral signature is changing quite a lot with respect to the one that I showed you before. And this is only for the snow. If you are taking the snow-free and the pure snow-free, you can understand that you can have different kind of rock, different kind of terrain with different kind of humidity, different kind of vegetation. You can have bloom, you can have whatever you can imagine is normal when you are going in the terrain. So, if we are applying state-of-the-art method on this condition, normally what is getting is quite erroneous. So just to give you a practical example, here we have an image acquired in January 2021 in the Alps. So you can see, first of all, that we have large shadows, and they are quite dark and quite big. And of course, for mountain terrain, this is quite common. Then I don't know if you see very well here, but we have atmospheric disturbance. So we have a little bit of fog, let's say. And then finally, we have what I told you, this snow glint on the southwest exposed slopes that are actually increasing the reflectance to a number that is actually bigger than 1. That is actually not possible. So if we are, for example, looking at the bands and the variability inside the bands, you can see that we have a different variability by considering all these different cases, and we may even have a problem in which classes of snow-free and snow-cover area are actually ambiguous at that point. But what is the most important is that we have a large variability, so we cannot really pretend that an NDSI index or a linear mixing using two N members is actually solving a big problem like this. Okay, so as I was saying you before, with the spectral variability, the easiest thing to do is to take L2 products that are normally topographic atmospheric corrected. And here we have an example of what this correction is doing. And as you can see, first of all, okay, starting from the good news, if we are looking on this area here, on the bottom part of the image, we can see that actually there was a quite good compensation, for example, of the sun glint area. So you can see that now the variability that we can see in these images is only due probably to the different in the snow types we have on the ground. But of course, on the other side, you can see that the shadows are not very well compensated, and moreover, the casted shadow, so the shadows that are not just on the steep or the hill part of the terrain, is actually still there present. And moreover, maybe not very clear from this projector and the quality of this projector, the fog that is here in this part of the image is still there, and plus is also altering the compensation of the reflectance in a wrong way for these peaks here. Okay, so what we can do, and here is the part maybe a little bit more new, and that can be also a tool for you. It would be nice to have a tool that is actually don't care about all this spectral variability, is not caring about how many classes you have on the ground, is not affected by the fact that you have shadow, that you have atmospheric disturbance, that you have anything, but with the only hypothesis to provide the full representation of the scene is actually able to identify the snow cover fraction. So here what we have done and what I wanted to show you is actually based on a theory that was developed many years ago, and is also the theory at the base of the support vector machine algorithm that we just modify in order to identify the snow cover fraction. But since this theory is not that easy to understand, I want to start with a very gentle introduction. So let's imagine we have a plane with two features here. So this can be one band, another band, or an index, another index, whatever you want, in which we have the snow and snow free that are that is possible to be divided using only straight lines. So here, the most powerful concept is that which straight line would you like to use to divide this problem? So you can draw a line like this, like here, where you would like to put the line. Close to this point, on the other point.
So the furthest away from both.
Exactly, in the middle between the 2 points. And so this is the very powerful, and now we will see also the very tricky to derive problem that we want to solve. So basically, we say that the best line is the line that is in the middle of the street. So here we have a street that has to be maximized, and we take a decision if a point, a known point, is actually part of this cluster of pixel or sample, or this cluster of pixel, on the basis of if it stay on this side or the other side of the street. Okay. So from a mathematical point of view, what we can do is defining a vector that is perpendicular to this straight line that we call W. And if we take an unknown pixel and we represent it as a vector, in this case, how I can understand with these two from a geometrical point of view if we are on one side or the other side of the street. It's simple also in this case. I just project this vector U on the vector W. So basically, by taking the projection that is done using the scalar product between vectors, so nothing very difficult, I can derive a rule. So that is very simple. So if I'm on this part of the street, this is snow-free. If I'm on this part of the street, I'm 100% snow. But very simple to say, very simple to imagine, but how I can solve an equation like this. As we were talking before, in this equation we have the unknown sample that we know actually, but we don't know anything about the vector W, and we don't know anything about the scalar C. So we are in the case we have infinite solution, okay? So we have to do a little bit of mathematics before. First of all, in order to understand what in this space is my mixed pixel. So my mixed pixel, it is a pixel or a sample that actually fall in its projection inside this street. So it's not either in this side or this side. So with a little bit of mathematics and without really lose any generality of the problem, we just put C equal to minus B. We just reverse this equation. And we start to reasoning about what is happening to the sample that stay on this edge of the street. So if I take the scalar product of the vector W with a sample that actually it is here on this edge of the street, and I put inside my decision rule here, I arbitrarily chosen that this sample has to be equal. Okay, first of all, if I take not only this on the edge, but all this one, has to be equal or greater and equal that +1. Instead, and this is an arbitrary selection of that all the sample that stay on this side is +1, or the sample that stay on the other side is -1. So if I introducing another variable that is called, or we called yi, and we say that this yi is +1 if the sample is snow, and -1 if the sample is snow-free, what I can rewrite this system of equation in only one equation where I multiply everything by y of I. So in this case, for the sample that are snow, this has to be, this yi is actually +1, and this has to be bigger than +1. For the sample that are snow-free, this is -1, this is inverted, so it will be less and equal to -1. So this system of equation is exactly written in this way using only one equation. So if we are just bringing the +1 on this part and we are considering only the pixel that stay on the edge, this is our new decision function that is allowing to say that if we want to stay on the edge of this street, this equation has to be true. So this is our first constraint. Okay? So just a little bit of math without any important part here. So we just know that the pixel that stay on these two edges has to follow this equation, and that's all. But we were saying before that we are interested in the fact that this width has to be maximized. So basically, we have to select, in order to select our separation plan, we have to select the one that is maximizing this width. But we don't know anything about this width. So let's start to reasoning a little bit about how we can compute this. And again, using the geometrical consideration, this become quite easy. So if we have a vector that is pointing to one of the snow-free pixel that stay on the edge, and another vector that is pointing to a snow pixel that is still on the edge, we know that the difference between these two pixels, it is exactly this vector here. That at this point, if I'm projected to the vector W, is exactly my width of the street. Okay, so that means that that actually I take this difference, just a little trick. I'm not multiplying by the whole vector W, but I'm multiplying by the unit vector of W, so it's just giving me the direction. And this vector can be calculated by taking W and divided by the magnitude of W. So I have the unit vector, that is this one here. So by projecting this on this, I obtain this width. Now, we have one important concept back here. We said that on the edge, this equation is holding. So basically, if I'm taking a snow sample multiplied by W, and I'm looking this, I have a snow sample multiplied by W, this yi is equal to 1, and this is equal to 0, so just taking on the other side, I take 1 minus b. And this is the first part of this equation. The second part of this equation is actually for the snow free. This is minus 1. So I'm taking this part, bring it to this other part, and it is plus b minus 1. So we have plus b minus 1 minus b plus 1. So that means that our width is actually 2 divided by the magnitude of W. Okay? Simple, very simple algebra. Okay, this is something very, very important. If you are following me until to this point, I think you were not thinking that this was possible. So the width is actually equal to 2 times the magnitude of our vector that is perpendicular to the street. At this point, we want, as I was saying, maximizing this difference. That is equal to maximizing this ratio, that is equal to minimizing the magnitude of the vector W, and as our numerical mathematician like, it is equal to minimizing this problem here, that is actually a quadratic problem like the one that we saw before. And of course, this has to be constrained to this fact that all the sample, the pixel that stay on the edge, has to follow this equation here. So basically, what we are in front right now is actually a minimization with a constraint problem that we normally, as you may know, we normally solve using the Lagrangian multipliers. So without entering really into the detail of what is a Lagrangian multipliers, I just give you an idea. When I want to solve a problem like this, of minimization constrained to this, what I can do, thanks to the theory of Lagrange, is actually taking my function that I want to minimize in this case, and subtracting the sum of all the constraints multiplied by the Lagrangian multipliers. So I obtain an expression like this that I have in this case to minimize. In order to minimize, I have to calculate the derivatives and put them equal to 0. Okay. So the first derivative of all the variables that are involved here, that actually are W, as I was telling you at the beginning, and B. And what I obtaining is something that is quite interesting, and it is that the vector W is actually a linear combination of the Lagrangian multiplier multiplied by y con I and multiplied by our sample. So basically, the vector W is just a linear combination of all the samples. So if I give you the sample, the one that, for example, if you are using a support vector machine, you are calling training, the vector W is just a linear combination of the samples, okay? At this point, we can do another step that is just taking this part, this vector here, and plug inside the equation and solving for L. So I take this part here, I take this, I'm exploiting the fact that this sum is actually equal to 0, and what I obtaining is this expression. And this expression, of course, and again, like in the case of the linear unmixing, I cannot solve in a closed form, so I have to handle to the numerical analysis methods that are solving this for me, and they are finding the alpha, so they are finding the Lagrangian multipliers. But what is very, 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 very interesting is actually that if I'm taking this equation here and I'm putting inside my my decision rule that I was writing here at the beginning, is actually coming out something like this. So basically, my decision rule is just a scalar product between my sample that I have. Okay. So what I can do with this, actually very, very little, because this is only solving a linear, very simple case like this. But as I said at the beginning, I wanted to solve something that is strictly nonlinear, so something like this. And for solving something like this, we have to use another very important part of the support vector machine theory, that is the kernel trick. So without entering into the real detail, the kernel trick is just applying to my dot product, the scalar product of all my sample, basically a function that is strongly nonlinear, that allow me to basically introduce other dimension to my problem until the point I arrive to a dimension in which the problem is linearly solvable. So at this point, with a simple solution of this equation, actually I can get my separation of the interplane. I can actually derive my decision function, and at that point I can connect this to the Snow cover fraction that I want to retrieve. Okay, maybe the only thing I want to add here, and we will see better in the practical exercise that we will have later, is actually that we don't have anymore only the alpha and the b that we have to compute here, but at this point we have another parameter that is called gamma. And to find this gamma, as we will see in the exercise, is not easy, especially if we are only looking at the overall accuracy, because the overall accuracy will be always at very, very high value, as we will see in the exercise. But what we can look at is actually the standard deviation of the kernel that is providing us basically the best value for gamma that is allowing us to minimizing the error that I'm computing. So just a very quick recap. We have our decision function, strongly nonlinear. We can take all our sample that can be snow-free, of different classes, rock, grass, whatever you are thinking. We can take our snow pixel that can be illuminated, badly illuminated, can represent very big, very small grain size, whatever. Take everything inside this problem, and basically we will represent them eventually in a space where everything is linearly separable, and the distance between this street is actually proportional to the snow cover fraction. Okay? Any question before going on? But I think during the exercise, maybe you can better put your hands and try to understand all this big theory that we have here. But I think is very good if you have at least an idea of how this is work. Is a tool that you can use anywhere in your, let's say, problem solution that you have. Okay, just to give you some example of how this is working, we are basically providing some result at this point here in one of the catchments that we are closely monitoring, close to our location in Italy. So we are basically very close to the middle of the Alps, at the border between Italy and Austria. And the catchment is called Valsenales. And in this catchment, we have the possibility to test our algorithm, not just this one, but all the algorithms, since we can also go and see if what we are doing is good or not. So here we have an example of one images acquired during the winter. So we have a lot of shadows, a lot of disturbance, as we were saying, from the illumination, the steep slopes, and so on and so forth. If we are taking the Copernicus Snow products, that is one product available in an operative way, and that actually is using the hyperbolic tangent that I was showing you at the beginning, one of the state-of-the-art method. Actually, the result that we obtain is something like this. So basically, what is happening is that it's struggling quite a lot on the identification of the snow cover fraction, especially in this big shadow area. Instead, if you are using, let's say, the machine learning approach that I presented you, there is a better representation of what is happening in the reality, especially on those areas. Here another example in the same valley. You can see maybe distinguish here the Intereisferner, a big glacier that is present in the Rofental, the valley that is close to Valsenales here. And the first thing you can notice here is that a Copernicus products basically where you find a big shadow like this one, even though here we have very high and most probably even you cannot see very well, we have a presence of snow is saying is snow free. Instead of our algorithm is able to show and correct this. And very interesting is also giving a little bit of sensitivity to the ridge of the mountain where are normally blown by wind, and so you have not that much snow cover in that case. Of course, as Biagio was mentioning, we need also to validate our data, so we went through a lot of very high resolution images that were acquired in different locations of the Alps mainly, in which we have a resolution for which we can reconstruct the snow cover fraction simply by counting the pixel covered by snow. And just to give you an example or an overview of all the different methods, basically in terms of root mean square error and bias, basically you can see that a linear mixing, like in this case, is performing quite nicely. We have a little bit of bias bigger than in our case. Of course, these two products can be merged, but in the case of, for example, state of the art, in this case, binary products, you can see that the root mean square error and the bias are quite big. For Salomonson, very interestingly, you can see that the root mean square error is not that big, but we have a quite big negative biases in this case. But what is the plan now is actually to move to the computer after the coffee break and try to replicate all these results. Okay, do you have any questions?
Is the Snowflake's product, is that available? And if so, at which resolution?
Actually, we are not providing the products itself, or actually in the Alps Snow project, we provide it for the Alps only for a limited time period. And it is at the resolution of 20 meters, actually, for Sentinel-2, yeah. But you have, now you have all the mathematical detail, and you will have all the code, so you can really replicate it if you want.
With the support vector machine, can you also include the estimation of cloud pixels, or do you have to remove it with other algorithms?
I mean, yeah. Actually, it is. I mean, one possibility is just, or as we are showing here, remove it before. So you just classify the clouds, remove them from the image as we show here, but you can also include inside actually the algorithm if you want.
Also related to the platforms, because for the Snowflake product, the platforms will be completely different than the Snowflake.
Sorry, Deb?
Like the Copernicus product has a completely different platform
Yeah.
than the Snowflake product. And I wondered about the different algorithms that are behind.
Yeah, I mean, there are two totally different algorithms behind, because I think the Copernicus is using, yeah, actually, good question. I don't know which cloud mask they are using actually in Copernicus.
Okay, but Snowflake is then the support vector machine.
Yeah. Yeah, actually, I think in this case that I just show you, we are using the cloud mask that is computed using the synergized code that is called sent to cloudness.
Okay.
So it's basically another machine learning approach. Coffee break.